Thank you. Hear me? Okay, it's a great pleasure to be invited to give a talk about particle physics here. I know many of you are. I'm not sure it's a mathematician or physicist. How many of you are physicists? Okay, no mathematician. Fine. Okay, easy job. Okay, so I'm going to talk about uh, portal for the future of particle physics, particularly for new physics. And two of the most important portals are the Higgs and neutrinos. And I'm going to talk about these two major top in China. So first of all, a little bit of review of standard model. So we know that all the matter are made of fermions, uh, 6 leptons and the 6 quarks. So you can see they form a very nice kind of 2 by 3 matrix. And their interactions are mediated by particles like photons, WZ, and gluons. And the theories to describing these kind of interactions are the electroweak and the QCD. And all of these particles have a mass coming from the field of the Higgs. Through the Yukawa interactions, all these particles obtain their mass. So this is kind of a very nice picture of our understanding of the elemental particle physics world. And they all described by this Lagrangian. So you have a theory, you have mathematics, and you have many, many of the experimental evidence. So see that to prove this is right, there were many, many Nobel Prize given to the achievement of this understanding of the particle world. So this is a great success. There were more than 20 Nobel Prize awarded for the establishment of this standard model, including theory and experimental discoveries, and also for instrumentation. There are also important achievements for the understanding to connect our particle physics world and the cosmology. So there were questions about the future. So is this the end of particle physics because every single particles has been discovered uh, uh, in the standard model, every single particle has been discovered, and are there any opportunities for young people? So standard model, although it's very successful, but it's not perfect. There were some experimental evidence that there are some hint of new physics beyond that. Of course, the first one is the mass of neutrinos, which is not within the so-called minimum version of standard model, and you need a way to extend it to include the mass of the neutrinos, and we don't know exactly how to put the mass of neutrinos into the standard model. And there are also experimental evidence which are actually in disagreement with the prediction of the standard model, including W mass. There were several 3 to 4 sigma kind of deviations from the prediction of the standard model. And from a theoretical point of view, there were some concerns. For example, if you look at the top quark mass, and the Higgs mass, you see that our vacuum stays in a metastable place. It's not at a very stable kind of comfortable zone. And also you see there's a perfect flavor symmetry between quarks and the leptons. And this kind of symmetry actually have no understanding about its deep root. And we also do not fully understand where the mass of Higgs come from. There were also a huge mass difference between the elemental particles, and many of the parameters in the standard model have to have some fine tuning. So it's not very natural. And also in the standard model, there were no places for dark matter particles, and also there were no sufficient large CP violation to explain the baryon symmetry in the universe. So most of the people, I think almost 100%, very close, let's say, I believe that the standard model is just the effective theory up to, let's say, 1 TeV. And RGC and high domain RGC can only also test standard model up to this kind of energy scale. So the question is, where are the new physics? Can we find new physics up to, let's say, between the 1 TeV to 10 TeV? So the future of particle physics run into three major categories. One is the constituent of matter, let's say quarks and leptons. And so we still have a lot of issues to be studied about the quark itself, its mass, diameter, and the spin of the proton and exotic hadrons. For neutrinos, we still have to understand its absolute mass. We have to understand whether neutrinos are Dirac-Majorana, and we have to see whether the lepton CP violation can actually generate baryon symmetry in the universe. And also, ultimately, we would like to see if there's any deeper world of the elementary particles. In other words, Higgs or these fermions are elementary particles or not. They may have a deeper structure. For interaction particles, first of all, we have to understand Higgs itself, and we would like to see whether you are able to unify the electroweak and the strong interactions. Showing this picture, you see that electromagnetic and the weak and the strong interaction, they do not coincide at the same place, like in this minimum version of the extension of standard model. So indeed, since the history of the particle physics actually is a history of unification. So starting from, you heard the talk by the other day by David Gross, that indeed unification is a major theme of the particle physics. We really want to have a unification of the electroweak with strong interactions, and ultimately with a unification also with gravity. And also we have an issue about the origin and evolution of the universe. In particular, with particle physics, we would like to find a place in our particle physics, community in our world, where the dark matter particle is and how it looks like. And also, we'd like to understand why in our universe there are no antimatter naturally existed in the universe. So can they explain by, say, leptonic CP violation? So all of these are actually issues we are working on, and we believe there are rooms for particle physics to proceed, and we do have a very good future. Let's talk about the first one, the Higgs. So Higgs is very important, and it generates mass for many of the for almost all the elementary particles in the standard model. But it also associated with the origin of electroweak symmetry breaking. And it also have issues about itself, the mass, whether it's natural or not natural, and associated with matter-antimatter symmetry. And in particular, it's a very good bridge to dark matter. Imagine that the dark matter has only a property of mass, and Higgs actually generates mass to ordinary particles. Whether Higgs similar mechanism has any connections with the mass of dark matter is an open question. And it's a very natural connection we can imagine between the Higgs and the dark matter. So indeed, in our international community, we do have a very good consensus among China, EU, let's say US, and also international committee for future accelerators. The consensus is that the Higgs factory is the highest priority for the future of particle physics. There were several proposals like CPC in China, FCC at CERN, and also International Linear Collider in Japan, and CLIC at CERN. So these are the two categories. There are two categories of the Higgs factories in the world. One is a circular collider. The circular collider has higher luminosity for Higgs, so you get better performance, and for less number of years to operate, you get a better precision. So indeed, it's very advantageous. And also for circular collider, you can reuse the Turner for the PP collider. So it's very good kind of continuation for the future of particle physics. Linear collider is also very important. If you really want to go to higher energy, let's say 1 to 3 TeV or even higher to 10 TeV for E plus minus, you have to go to a linear collider. It's the only way. So linear and the circular both have their very important advantages. And for the moment, if you limit your energy of the beam to the Higgs, these are the comparisons. So the luminosity, you can see that circular is much higher than linear, and the cost, indeed, if you do it in China, is much less than in Switzerland. And also comparing to other machines, the linear collider is still cheaper, and the construction is also can be earlier. Why we choose 100 kilometers? We have a study of performance cost ratio, and you can see that the minimum or the cheapest way to generate the Higgs is actually at about the circumference of 80 to 100 kilometers. So that's why we choose 100, because 100 also gives us a little bit more room for the PP collider. So anyway, 180 is optimal kind of circumference. There are also other options in the world, for example, linear colliders in the United States, so-called the C-cube. There are also other options of the linear colliders with the energy recovery scheme. There's also another proposal to use a plasma weak field acceleration called half, which also can be considered as a good option for the Higgs factory. But they use this kind of a very new technology, which is not yet mature enough, and people believe that it takes another 20 years really to be able to realize it. And also people were talking about muon colliders, and this is actually the future plan by the National Academy of the United States as the future planning for the years of 2040-ish. So that's long time from now. So why we talk about the Higgs factory here in China? Indeed, in the year of 2005, we were thinking about the future machines after BPC2 and BESS3. BPC is Beijing Electron Positron Collider, operational since 1988. So this is actually the machine we have been working on for almost 40 years. So indeed, this is a small machine. I mean, we believe this is going to reach its end of the life. We should find something new for it. And after discovery of the Higgs, we realized that there's new opportunities for us to have a continuation of the future of the particle physics in China. And this is the ideal kind of successor of the BPC2. And this idea of the CPC followed by possible super-proton-proton collider in the same tunnel was actually officially proposed in September 2012 and reported at the workshop in Fermilab the months after. So indeed, this becomes a very hot topic immediately after it was reported and quickly gained momentum in China and also in the world. CERN, in almost 3 months after that, started the FCC program, immediately followed this approach because everybody quickly realized that this is the future of our field. So starting from 2013, we started really to work on this project. So we had the kickoff meeting, we have a conceptual design report, and also we finished our technical design report in about 2 years from now, 2 years before that. So the scientific objectives of this machine actually can be summarized in these slides. Indeed, we summarize all our physics goals in these 5 white papers. 3 of them have been mostly finished, and 2 of them are still under study and to be published very soon. So in a few words, let's say, Higgs coupling can be measured in this machine with better improvement of with improvement of almost 1 order of magnitude. So you can actually have a much higher precision, up to, let's say, 1% or even less. And with the 1% precision of the Higgs coupling measurement, you can also probe new physics up to about 10 TeV, which is a factor of 10 higher than high luminary HC. And you can also improve the electroweak measurement by a large factor. So indeed, you see that this is the test of the scales of the new physics we could reach. And you can see that many of these tests can go all the way up to, let's say, 10 TeV. And for a few, let's say, physics topics, we had a detailed study, of course, sometimes model dependent. You can see that for dark matter, we can do a very good job here, all the way down to the level of 10 to minus 18 for the coupling. And this is already better than, say, the dedicated underground experiment. And we also have many other searches, and also for the Higgs self-couplings and so on. So the design of the machine is the following. We already mentioned that we have a baseline of 100 kilometers circumference. We use this tunnel for both the electron machines and also for the proton machine. So the tunnel has to be large enough, 6 meters of the width. And we are going to use 30 megawatt as a synchronous radiation power for the baseline, and upgradable to 50 megawatt, and high lumi Z and TT bar. We can switch back and forth for different kind of energies. And also this machine is a very good high energy synchronous radiation facility. So this is a comparison of the CPC with other dedicated gamma ray factories, kind of. And you can see that the flux energy is actually exceeding most of the dedicated light gamma sources, except the LCS2, which is, of course, everybody knows it's a big machine, and we are a little bit, let's say, less the energy, but the flux, actually, we are in a very good shape. So this is actually a dual purpose machine we can use for many other applications. In the last several years, we finished our technical design report. The total sum of the cost of this machine is 36.4 billion RMB. So this is 5 billion euros or dollars, whatever unit. And this is actually almost factor 3 cheaper than the one in Switzerland for the BICER. So indeed, this machine was not just designed by paper. It's based on our 40 years of experience on accelerators. First of all, we have this BEPC, Beijing Electron Positron Collider, and then we are actually stable running this machine at about 1 amps of the beam current. The machine running at 1 amps beam current is very, very difficult. You all know that right now in KK, they have very close 2 amps machine of the beam current, and very, very difficult to reach the luminosity. So we designed this CPC at about 1 amps, and we do have experience with 1 amps kind of the machine and the stable running. We are also working on the light source, which is actually only a few kilometers from here. If you're interested, you can have a visit. And many of the technology are actually exceeding the requirement of the CPC. So we do have already some kind of practice or even medium scale of the prototyping for the technologies needed for the future CPC machine. So we come up with a summary. You see the list of tables, and these are the fractions of the cost. The biggest cost is a magnet, and then it's a vacuum. They occupy almost 50% of total cost. And then the rest of the components, we had R&D of almost 100% of all of them. And a few exceptions here: IF power source, control survey, and the magnets. Except that, everything has been prototyped, and you can see this kind of equipment. They all exceeding our specifications. So before the construction, we have a few items we had to finish. So this is the whole list. we have a total of 35 working groups. I will pick a few examples here. So example one is the S-alpha cavities. So this is, of course, the most important component of the future accelerator, actually applicable to almost every machines to be built. So during the TDR phase, we had several prototypes, including a short module for the 650 megahertz and a full module 1.3 gigahertz. So we would like to finish a full long module of 650 megahertz kind of cavities. This is actually start construction. Short modules, we have already demonstrated that they exceeding our specification. These are the specifications and these are the testing results. You can see that we are way above the specifications for the machine we designed for. Second example is a klystron. Klystron is generated with generate power for the microwave of the RF cavities. So the first important kind of parameter for this kind of klystron is the efficiency, which tells you that how much of the energy from the wall to the microwave you are going to use. So this efficiency, of course, is very important for the power consumption. Right now, the typical value of the efficiency is 60%, and during the TDR phase, we managed to achieve the world's best result of 78%. And now we are working on an even better version with efficiency more than 85%. A small test shows that indeed with the energy recovery kind of scheme, we can achieve 88%. So in the next few months or so, a year, we're going to build another big prototype like this to aim for efficiency of 85%. The third example is automatic production of the magnet. I mean, right now, everybody in the past 100 years making magnets by, I wouldn't say by hand, but by piece, let's say one by one, by people. So in the future, because of the cost, you remember 27% of the total cost is the magnet. So by people, I mean, of course, they can only work 8 hours a day and 5 days a week. So we would like to, first of all, speed up the construction speed and also reduce the total construction time. And the most importantly, we would like to reduce the cost of the manpower. So this cost is very, very high. Even China, we are not able to bear the labor cost. So by using this automatic production line, we can actually reduce the cost by almost 30 to 50%. So this is a design, and the prototyping has been started, and we are going to have a commissioning next year. For the detector, we came up with a design, and we have silicon tracker, TPC, and calorimeter, and so on. So I'm not going through too much of the details. Just give you two examples. First of all is the electromagnetic calorimeter. In the past, you have two choices. Either use the crystals or you use the sampling calorimeters with the silicon or scintillator. But crystal calorimeter can give you very good energy resolution, but not the position. Sampling calorimeter give you very good position, but not the energy resolution. Now, if you want both, we came up with the idea to arrange crystals in the XY direction instead of the Z direction towards the beam interaction point. So by arranging it in the XY direction and the particles coming in with a particular mode towards this crystal arranged in this kind of perpendicular way, and we can get both energy and position resolution. So this shows that we can actually separate showers at the distance of about a few centimeters, and we can get a very good resolution of 1.3 or less than 2% over square root of E. So this is almost a factor 10 better than the sampling calorimeter and more or less the same position resolution as a sampling calorimeter. So this is actually a very good way to actually achieve both the energy position resolution and also at the same cost compared to the silicon option sampling calorimeter. For the hadron calorimeter, we came up with the idea to use a high-density glass scintillator. So in this case, you can improve your sampling ratios to 30% instead of 1 to 2%. So by doing this, you can have a very good energy resolution, which is almost factor 2 better than typical traditional hadron calorimeter. The trick is to have very high density glass scintillator with good light yield, because typically the glass scintillator has very little light yield. You see from this graph, you see these are typical kind of world record of the light yield from a glass scintillator with density of 6. And we managed to produce samples which can generate almost factor of 10 more light from the same kind of density. By doing this, you can build a very compact hadron calorimeter and a good kind of energy resolution. So this is something we're actually working on, and we believe it can be very, very useful and advantageous compared to other options. So towards the future of particle physics, of course, we very much rely on the accelerators. There are 2 or 3 different kinds of possible technologies. One is, as I just mentioned before, circular collider. Another one is a linear collider, and another one is a muon collider. So mature technology, both for the circular and the linear colliders, you need something like 100 kilometers or 20 or 30 kilometers, going all the way up to 250 GeV. And you need technology like superconducting RF and superconducting magnet. These are both existing. I just demonstrated that. We do have prototypes which actually succeeding our expectations. Now, for the future, for the circular collider, it's obvious that you use existing tunnel, so you want to go to circular proton-proton collider in the same tunnel, and you had to improve your superconducting magnet technologies. And if you go to a linear, the only way you can go to the next stage is longer linear collider and going to higher energy, let's say 1 TeV or 10 TeV. And you had to have technology like plasma weak field acceleration or the energy recovery kind of technologies. So these are all the new technologies people should have some control towards the future, and these are the mature existing technologies. So what we have chosen, the path, is starting from the circular electron positron collider and then go to the proton collider, but not forget about these technologies. So we decided to go this way. And muon collider is much more difficult. You need a 60 phase phase-based cooling and fast acceleration. And also you had to worry about the neutrino radiation. I mean, everybody knows that neutrino is harmless, but for muon collider, you have to worry about neutrino radiation. So that shows how difficult it is. So what we are doing, instead of what I mentioned before, for the E plus minus, we are actually working on technology for the future proton-proton collider. The most important thing is a high TC superconducting magnet. You have to use the new technologies. If you use the existing one, of course, it's going to be way too expensive for 100 kilometers. Using new technologies, we have to resolve issues. So there are 2 choices. One is iron-based, another one is copper-based. But copper-based is a ceramic, and iron-based is a metal. So you can easily imagine that the metal kind of cable is much, much easier, cheaper, and useful for the future. So we are working on the iron-based superconducting materials. We believe the cheap, and we actually achieved the world's longest cable, the best performance, and also the world's first iron-based superconducting coil. You see the improvement in the last 10 years, starting from 2016. We are actually now here, And we still have some distance to the goal, and the goal is somewhere here, which is way better than copper-based current limit. And this is a low temperature kind of stuff. So low TC actually cannot go to very high magnetic field. So if you have to go to a higher magnetic field, you have to go to high TC, and you have to choose a cheap one. And iron-based, to my mind, is the only choice. And you have to figure out the technologies and in the next 20 years. And this is actually needed preparation time. And so business time, if we work on the E plus minus, this is just ideal kind of roadmap towards the future. We did not forget about the linear collider, because this is the only path if we really want to go to, say, 1 TeV or 10 TeV. So if you want to go to 1 TeV or 10 TeV, if you use the traditional technology like RF cavities, it's going to be too expensive. So you have to have new technologies. The new technologies is so-called plasma-based weak field acceleration. Up to now, this is just a kind of mechanism. There's no accelerators based on plasma. So we came up with the idea to use this plasma as an injector of the CPC. So by doing this, you overcome problems we had up to now with the plasma, because the quality of beam is not very good. We use traditional accelerators before and after to improve the quality of the beam, but use plasma to save the money and save the cost. So by doing this, you get the benefit of both, and you can actually utilize the plasma for the future accelerators. So we came up with the design, the simulation, everything seems fine, but we need some proof. So we actually modified our Beijing Electron Positron Collider, the LINAC, to be a test facility for the future plasma accelerator. So by doing this, we can study, for example, cascading, positron acceleration, and also electron gun, laser, and so on. By doing this, we prove that it is feasible, and then we could use it as a CPC injector. This is just an option. If we are not able to finish on time, we will use traditional technologies. But if we are able to finish this very soon, we can use it for the future CPC injector. So you see, we actually remodeled our lab, and the things are going up. So in the next 2 or 3 years, we should have some results. So this is CPC planning. We hope we can start construction around the year of 2027. And then after 10 years, we finish construction. And before 2040, we should have a running machine. So this is almost 5 to 10 years earlier than FCC planning. So now let's move to neutrinos. We see that neutrino plays a very important role. It's almost 1/4 of number of elementary particles. And these are only particles which have a property not consistent with standard model. And we had to figure out how the neutrino mass are generated, and whether neutrinos are itself its antiparticles. So indeed, this is a very important topic in particle physics and also in astrophysics, because it's so abundant that it could easily affect the evolution of the universe. So neutrino oscillation is actually the most sensitive probe to the neutrino mass. If you look at the neutrino oscillation, the formula, you see the mass appears here as oscillation frequency. So if you see neutrino oscillate, it's approved that neutrino has a mass. Although the mass you can measure is only a relative mass, the mass difference, not the absolute mass. But anyway, neutrino oscillation is a very interesting, very important phenomenon of the particle physics. It was discovered in the year of 1998 and also the year of 2002 for the atmospheric neutrino oscillation and the solar neutrino oscillation, respectively. By these two experiments, they measured these parameters, θ2 and θ1, θ23 and θ12, and also their mass difference. You can see once you measure this, you get theta and delta m squared simultaneously. very recently, in our experiment in diabetes, we actually measured for the first time the value of theta-1,3. So you can see that by the time now, indeed, we're still missing two parameters. One is the mass hierarchy or mass ordering. Another one is the CP phase. So our Juno experiment, which is constructing right now and will be finished very soon, is actually our continuation of the diabetic experiment using liquid scintillator. And it can measure the neutrino mass hierarchy if we put our detector here at the oscillation maximum of theta-1,2, which is about 60 kilometers from the reactor. Diabetes is here, which is only 2 kilometers. You can see that there's a factor of 30 difference of the baseline, which means that there's a factor of 900 difference of the neutrino flux at your detector. So your detector has to be much, much bigger than a detector if you place at 2 kilometers. So these are the complication difficulties. The idea came out in around 2008, and the construction started in 2015, and the data taking will happen this year. The main difficulty is summarized in this table. You see, first of all, it's a mass, because we had to have a big total mass to combat with the problem of the neutrino flux. So this is almost a factor of 20 larger than previous one. Comparing to diabetes, it's almost a factor 1,000. And then we had to have enough light, because energy resolution needed is about 3%. And you compare to others, you see there's a factor of 2 difference in energy resolution. So you need a factor of 4 more the light coming out from your detector. So these are 2 major issues we had to overcome. So this is a design where to find out a place which has, okay, I forgot to mention this one. Our idea is to put our detector at the equal distance of 2 reactor complexes. So in this case, you can use 2 reactors instead of 1, so you can reduce your detector size by a factor of 2. So this is a way to save money for your detector. So we find the location in that place, shown before 60 kilometers, and we have this underground laboratory, and fortunately, this 60 kilometers and equal distance is actually underneath a mountain. So, I mean, we can build our laboratory. And indeed, this piece of rock here is a granite, so we can actually safely build a very large underground cavern. And it took us 6 years to build this underground cavern. And then afterwards, we start to build or assemble our detector. So as I mentioned, the underground cavern is 50-meter diameter, 7 meters high. It's larger, slightly larger than Super K, and smaller than, let's say, Hyper K. Diameter is almost same, but Hyper K has higher height. It's more like a cylindrical kind of shape. The detector is made of 20 kilotons of linear alkylic benzene plus PPO plus PSMB plus BHT. So this is formula of the liquid scintillator. And the detector is 35 meters diameter acrylic tank made of 260 pieces of panels. So we build them one by one and glue them all together. This is how it looks like. And when we finish the construction, you see people were trying to inspect defects on the surface of the acrylic. So this is how we build our detector. We start from bottom to build the steel structure. And this steel structure holds the acrylic panels. So you can see we build the acrylics from top to bottom. It took us almost 3 years to figure out how to build this. And finally, we concluded that we should do this way because it's much more easier, safer. If you from bottom up for the acrylic, you may end up troubles. If you drop something, it destroy your already built acrylic and also for the tubes outside. So from top to bottom is actually easy way. And we have a platform you see in this middle for people to stand on and to build this acrylic. So this is how it looks like when we finished. We installed the 20,000 PMTs, in which 5,000 coming from Hamamatsu, another 15,000 coming from a Chinese company called NNVT, which has a higher detection efficiency. And also we have a 25,000 3-inch PMTs in between. So total, we got a photo cathode coverage of 78%. This is very important for the energy resolution. So this is already what we could achieve, the maximum. The clearance between the two PMTs is only 3 millimeters. So you can imagine how difficult it is from point of mechanical structure and so on. So this is how it looks like when we finish. This is from the top, and this is you see from the bottom, the size. And Juno is a large international collaboration with 700 members from 72 institutions and in 17 countries and the regions. So we finish this critical tank construction, and then we start to clean it. You see, we had to. This is size. I mean, and the size is very, very difficult. So we have to invent many, many things to figure out where people stand and where people can work, and how to access to places you want to access to. So this is the way we do in the cleaning, and we invented this system and made it clean indeed. And during the construction, of course, it's very difficult. And when we finish, we have to fill the water. The acrylic is very thin. It's only 12 centimeters, a 10-story building. So it's much bigger than this building. This building is probably 5-story or something. So it's big. So everything is very fragile. It's even thinner if you compare the volume of egg and its shear thickness. So it's very, very fragile. So we very much worry about the structure, stability, and the safety. So during the feeding, you have to guarantee that the level of the liquid is the same. Exactly inside or outside is the same. Otherwise, you destroy your acrylic sphere. And you also have to make sure that the atmospheric pressure inside outside is exactly the same. Otherwise, it will explode. And the temperature has to be the same. Otherwise, with temperature variation, it can easily explode. So we managed to control everything and make sure that the air inside outside is well connected so that there will be no air pressure difference. What easy to control, but the air difference is air pressure difference is very difficult to control. And also, in addition, for point of view of cleanness, the sphere inside, after the cleaning, the washing, you see it before, they cannot see air. Air is very radioactive, and the radon decays can completely destroy the requirement of the radio purity. So we should make sure that when they breathe, they suck nitrogen, and when they go out, if the pressure is higher, they push out the air or nitrogen. So it's two ways, and you have to make sure there's this kind of breeze using different air and using different channel. And you have to make sure that it works just as you designed for. So we have supporting bars, we have a supporting structure, and we have sensors. We measure the stress. You can see over the level, the bottom didn't change very much, and the top changes a lot. That's because the oil is lighter than the water. So the ball, when you fill it with liquid that goes up, so the top has to push the ball down. That's why the pressure, the press actually is very, very high. So with this simulation, you can see that they agree well with our calculation. So we know that the whole sphere is safe and can satisfy the requirement, and we are able to continue our experiment. So in addition, we have to fill the ball with a liquid scintillator. So we have a storage tank, purification system using aluminum oxide, distillation, and then we have mixing plant to add the PPO and the BSMB. This is the oscillation, this is the scintillation kind of materials. And we have a water extraction system to remove radioactive impurities, and also gas stripping system to remove radon and oxygen. And then we take some samples, measure whether it's okay, and then we put the liquid into the detector. So it's complicated. You can see the scale chemical engineering kind of equipment. So we finished everything, managed to fill the detector with liquid. We are right now here. We are still missing something like 5,000 tons of the liquid. And what we have obtained from the testing showed that the attenuation lens, light yield, uranium thorium kind of background also, and so on, are all satisfying our requirement. And in particular, you can see this requirement, 10 to minus 16 gram per gram. It's about 10 milligrams of dust in your 20 kilotons of liquid scintillator. So this is a very, very difficult and stringent requirement in this. So few minutes, I can show you a video which can give you an impression how the construction process, where you start and how you get it finished. This was the first time as digging. We had an enormous trouble with the water underground. And the flux is about 500 or even 600 cubic meter per hour. Several million cubic meter water per year. So the digging actually took us more than 5 years. Original planning was 3 years, so the way exceeding our expectation because of this water problem. This is the stainless structure. This is actually the largest stainless structure in China, 40 meters of diameter. And then this middle plate platform is used for installation of acrylic. It can move up and down and change the diameter. And the precision of this steel structure is roughly a few millimeters. Otherwise, you are not able to install your phototube with a clearance of 3 millimeters. So this all required with a very high precision. See, its panels are arranged in a circle and then pushed up and glued together between the panels. This is almost finished, yeah. This is a platform. Yeah, this electronics, they all embedded into the water, so they have to sustain 40 meters water pressure, make sure there's no leak. So that there's the lip welding and test it in the world deepest swimming pool in Italy, 40 meters deep. Yeah. So the physics have a very short summary. Uh, we can measure the mass hierarchy with roughly 6 sigma and independent CP phase. We can measure neutrino mixing parameters to less than 1%. You can see that this is the current precision. And for 100 days, we can improve by a factor 2 or 3. And for 6 years, we can improve almost by a factor 10. And this precision is way better than what we have measured for the quarks. The quarks, after many, many factories, 5 factory, B factory, C factories, we only measure that about 1%. So this sub-percent kind of precision is very important for the understanding of the neutrino unitarity and for search for new physics. And we can study the burst supernova neutrinos. If 1987A happened again, we could see 5,000 events instead of 10 or 20. And we can discover diffuse supernova neutrinos. We can study geoneutrino to separate the different models. And also we can study solar neutrinos with a better precision than Bolexino. And we also can search for proton decays. We also have a near detector as a reference detector, which has a lot of very good features. I think I'm going to skip. I just show you the last slides that after we finish the neutrino oscillation, we are going to upgrade this detector with double decay isotopes. We can choose xenon or tellurium at a total mass of about 100 tons or 50 tons. By doing this, we can actually have a much better precision than any of the planned double bit decay experiment. You can see that we are almost the best in the world. So indeed, this is the experiment actually have a very long lifetime of roughly 30 years. So summary, Higgs and neutrinos are the two most important portals for new physics. Joule and the CPC have a very good standing at the forefront of the field. So we believe we have a very good future, even though we encounter pessimistic views, opinions, and people, and also sometimes disappointing events. We think that in international collaboration also is very important for high energy physics. Thank you. Yes. Yeah, it is not decided, and there are several different places in China. We did geological exploration in 7 different places. Of course, we have our preferred site, but it's up to the negotiation between us, the new local government, and the central government. Yeah, I mean, we already started the geological investigation. Yes. Yes. We believe that the 15th five-year plan will start very soon, and we are going to submit our proposals through this process. And within a year or two, I think the 15th five-year plan will be determined, and hopefully we can get approval. That's the hope. Yes.
Yes, please.
Yes. Right. So traditionally, hadron colorimeter are made of uranium or steel with some sampling the active materials. Use glass, because of high density, you can actually think about full absorption or even full absorption detector with a much higher sampling ratio. So it could have a much better performance with some sacrifice of the density. 6 is very close to a typical kind of density, average density of 8 or something. So it's not much far away from what people have achieved in the past for the density. And the glass is not a crystal. Of course, it's hard to imagine you use crystal hadron colorimeter. It's too expensive. Crystal can go all the way to 8 or even better. So in the past, people actually imagined that or hoped for to build a full absorption crystal hadron colorimeter. So using glass, of course, you cannot do big crystals, and glass has a very poor kind of transparency. But because of needed position resolution, you can actually make small pieces. So in this case, you overcome problem, the hadron, let's say glass, which doesn't have too good transparency, small pieces is good enough. And coupled with the modern technology of silicon PM, which is very cheap, almost factor cheaper than people have been used in the past for silicon diode and so on. So in this case, each one have a small silicon PM coupled. You increase the number of channels compared to the let's say big crystal colorimeter, but the glass is so cheap. Indeed, if you put everything together, it's still much cheaper than a full absorption glass colorimeter. A little bit more expensive than the traditional kind of scintillate, plus scintillator, or the with the sampling colorimeter. But it has much better performance. So we believe this is a good choice. We did testing. It's okay. So for EM colorimeter, sorry, for the electron positron collider, the radiation hardness requirement is not that high. So for hadron machines, you may have problems, but for electron machine, it should be okay. Economy is slowing down a little bit, but the just slowdown of the growth rate. The GDP is still going up. And the government did have a plan to increase the fraction of R&D over GDP. So GDP is going up, the fraction of GDP is going up. And also the government has a planning to increase the fraction of basic science over the R&D money. So if you put all this money together, indeed, there's a very conservative estimate that by the time 2035, the money for the basic science is going to increase at least by factor 2 or maybe by factor 3. So I think just simply talking about money is not really the major issue. The major issue, whether this is the highest priority or not, I don't think there's a shortage of money. If we don't take it, somebody else will take it.
Thank you very much for your answers. And again, let's thank speaker again.
Thank you.
We have 10 minutes.